Anyway, let us begin. Today's lesson is the last lesson we have in this unit. It is on Newton's third law. Newton's third law states every action has an equal and opposite reaction. Or if you want to put it to the Hamilton cadence, every action has an equal opposite reaction. It is, I think, the most poetic of these laws. It, fits very nicely in the middle of a rap. Unfortunately, it's also one of the vaguest. Like, what the heck does any of this mean? Some of those laws make a lot more sense. You can parse them really clearly. This one takes a little bit of interpreting. So let's talk about what this actually means. When we say every action, what the word action means here is every force. Anytime there is a force that is being applied, regardless of what type of force it is, all of these different types of forces this is going to be true for. So every force, so that word right there is just meaning every force has an equal in strength. So we're talking about like how many newtons has an equal in strength. And opposite, this opposite means the direction of the force. So opposite in direction. Opposite in direction, reaction. And then this reaction here is referring to another force. This is like force number 2. This is the second force that balances out each initial force. This is my annotated version of this. I want you to take, today's going to involve a lot of thinking about things that have happened in your life and recontextualizing them with this law. So let's start with something simple. I want each of you to take your hand, curl it into a fist. Do not actually do this because I don't want anyone to hurt themselves, but mentally imagine yourself punching a concrete wall as hard as you can.
Ow.
Yeah, ow.
Ow.
Right? I see some of you miming out, shaking your hands in pain. Right? This would be an unpleasant experience. Yes, Yossi?
Is that because the force that you bring against the wall comes back at you?
That is exactly correct, Yossi. However hard you punch that wall, the wall hits you back exactly as hard. You have to genuinely be careful throwing a punch because you can literally injure yourself punching a different person. Right? It's very easy to literally break your hand punching something because however hard you hit something else, you also get hit equally as hard. Audrey?
It's also a bit of a metaphor too, because something that comes back a lot as back at you that you do to someone or whatever.
Yeah, metaphorically speaking, engaging in an act of violence not only does harm to other, but also harms you and your own soul, right? Engaging in violence is a thing that can be damaging to you as an individual as well as to others. That's true in the metaphorical sense, but it's also quite literally true. Like maybe you punch somebody and you break your hand, right? Lisa?
Well, at least if you punch someone and break your hand, then you know that they probably broke their face too. So you did what you wanted to.
Right. Eye for an eye makes the whole world go blind. All right, so this is an example of something that in physics is called a force pair. So another way of stating Newton's third law is to say forces always come in pairs. So forces always come in pairs. There is an action and there is a reaction. And there is a technical term for these pairs of forces. We call them force pairs. It's a very convenient term. For once, they didn't make up something weird to describe things. It just is literally what it is. We call these force pairs.
Wait, what's the and symbol?
The way you draw an and symbol is you start at the bottom right, you go up, and then over like this, and then through like that. That should be a little bit smaller. That's an and symbol. But you can also use a plus. If you want a really simple way of drawing it, some folks will just do that. Right? The important thing is that you be able to understand your notes. That's what really matters. example of a force pair could be this idea of when you punch the wall punches back. So for example, when you punch the wall punches back. These forces are equal in strength. However hard you hit the wall, you get hit back exactly equally as hard. Whatever direction you apply that force in, that force gets applied back in the exact opposite direction. So it is equal in strength and opposite in direction. Your action and your reaction. Now, once you understand Newton's third law, you can begin to understand a number of unpleasant / humiliating circumstances you might have experienced at various points in your lives. How many of you have skateboarded at some point in your life?
1 point.
All right. So literally every person who I have ever seen get at all close to a skateboard has done the following thing at least once. You stand on the skateboard and then you decide you're going to take a step forward. Who can tell me what happens when you do this? All right, tell me all about it.
The board flips over.
Yeah, the board flips. In which direction does the board go? When you step forward, the board goes.
It goes back and tries, and it's like, either it flips towards you or it like shoots back.
Yeah, they like shoot out back behind you, and you typically go like straight into a faceplant, right? Forwards. This is because when you take a step, you're applying a backwards force, right? When you step forwards, you're pushing backwards on the earth. If what you're standing on isn't a massive planet that would take huge forces to move, but instead a teeny tiny skateboard, then yeah, it's gonna shoot out from underneath you. How many of you enjoy like messing about in boats?
No, I love.
All right, a little, slightly fewer boaters among you. Those of you who've ever boated, have you ever had the experience of like trying to step off the boat onto the dock?
Oh yeah.
Right? What has happened during that?
There's a boat it like tilts.
Yeah, the boat like moves back or bobs down. It moves away from you. And there's like, it can actually be quite dangerous. It's entirely possible the boat slips out from underneath you and you can like come crashing forward and hit your head on the dock. Right? That is like a common cause of drownings. You know? It's a really dangerous thing because the boat, when you step forwards, what you're actually doing is you're applying a backwards force to the boat. And since the boat is not that heavy, it slides back, you end up face planting, instead of stepping neatly onto the dock, you end up stepping into the water, best case scenario, or slamming your head onto the dock, worst case scenario. Emily.
So theoretically, if a mouse stepped on it, what would happen?
The force
Step
would be
off.
so small that you wouldn't notice the boat moving much. In the same way that when you just take a normal step forwards, you're applying a backwards force to the planet, right? I apply a backwards force to the Earth, but the Earth is such a massive object. Remember, force equals mass times acceleration. Because the mass is so huge, the acceleration is minuscule, so tiny that you would never notice it, right? Let's go to Audrey, and then we can go to Joaquin.
One time we were trying, like I brought my dog in like a boat, and one time we were trying to park the boat, and my dog has like, well, this is like my old dog. He had like a ton of hair in his face,
Mm-hmm.
and yeah, it's the same type of dog. But the dog, he ran forward without realizing what was going on. He fell into the water.
Yes.
And it's kind of funny.
Yeah. Trying to step off a boat and ending up directly in the water is a thing that has happened to many people at many points in time, right? And it's because of Newton's third law. Once you start noticing it, you can see how all of us are moving through the universe with a series of like pushing and pulling on our environment in order to move us around. One of the easiest places to see this is swimming. Raise your hand if you're a swimmer. All right, lots of swimmers here. Can I have those of you who swim, go ahead, stand up and just like mime for me a front crawl, that like freestyle thing. Yeah. Yeah. All right, right, so think about that motion.
You're like clawing at the water and moving it back to push it forward.
Yeah. When you are swimming, you make your hand into a little cup so you can push on the water as effectively as possible. Once it gets into the water, you like make this cup and you grab the water and you push that water behind you. And when you're moving your arm forward, that part's when your hand is out of the water. So you're not pushing on the water when you're moving your hand forward. And then when it's coming back through, again, you scoop that water. You push the water behind you. So you push backwards on the water. And the water pushes forwards on you. It is the water that moves you forwards. You do not move yourself forwards. The water moves you forwards. Yeah?
How can you grab onto water?
You're literally pushing on it.
You take a cup and then
Right? Think about how different it is to swim.
ice cream.
No. Nine. Think about swimming like this versus swimming like this. Which one's going to get you farther?
The other one.
Yeah, spoons, not forks when you're swimming. Right? And it's because, like this, you can actually catch the water. Like this, it's just slipping through your hands.
Like if you have a drink and you take a spoon, you'll get more than a fork.
Exactly. All right. So another example of one of these force pairs is to say a swimmer pushes backwards on the water. And the water pushes the swimmer forwards. Yes, Nine.
So it's basically like the harder you push, the faster you go.
Yes, that is exactly correct, because these two forces are equal in strength and opposite in direction. So the harder you push on that water, the harder the water pushes on you. If you look at like really good swimmers, like their torsos are jacked, right? Incredibly strong like shoulder and torso muscles, right? Because the harder they push, the harder they get pushed back. Has anyone here ever like had an altercation with a goose?
Yes.
Kinda has.
Right. Those of you who've had altercations with geese, they're scary. Like truly
They're
frightening
terrifying.
creatures. Right? Fun fact about geese. Let's say a swan. A swan's breast muscles, right? The muscles of their torso, the ones they use for flight, they are literally strong enough that if a swan flaps its wings and hits you, it can break your arm. There are multiple cases of birds, swans and geese specifically, literally breaking people's arms because of how strong their wings are. And they have to be strong because think about what a bird does. When a bird flies, it's kind of like you swimming, right? Their wings make these big scoops, and they have to push down with enough force on the air. They're pushing down on the air, strong enough that the air's force pushing back on them is enough to lift a swan off of the ground. It is enough strength to literally break a human's bones, right? These are strong birds. I have a tiny parrot that's like this big. It hurts when she flaps her wings and hits me in the face. Like it is an unpleasant experience. Even just tiny little thing that she does. Yes.
So for a swimmer, like the harder they push, so that's like the secret for professional swimmers.
Well, there's two secrets. One is just plain strength, right? The more force you push with, the more force you get in the opposite direction. The other is technique, right? Because if you're just like flailing in the water, then you're kind of pushing in all directions, so you're getting pushed in all directions. A really good, capable swimmer is going to be having such a good technique that they're like pushing all that water directly behind them, so that they go directly forwards. And when they're resetting their arms to get back to that original position, they're moving as little water as possible, so they don't get pushed backwards, basically. They don't slow themselves down. So it's all about, like, literally equal in like the strength, because the stronger they push, the more they get pushed back. And thinking about the fact that it's opposite in direction. So they want to be pushing in the correct direction. That's where like the good technique with swimming comes in. Make sense? Yeah. All right. So another example of this force pair is a bird pushes down on the air, and the air pushes up on the bird. That's another force pair. Do y'all remember that video of the vacuum chamber in Ohio with the bowling ball and the feather?
Yeah.
All right, I want you to give yourself a little bit of imagination around that. I want you to picture a tiny songbird, right? You have a beautiful little songbird in your mind's eye. Now I want you to put that little beautiful songbird in a little birdie spacesuit so that the birdie will be able to breathe in the vacuum chamber, okay? Can everyone imagine a little tiny songbird in a little tiny bird astronaut suit? All right, you got that adorable picture in your head. All right, take your little adorable birdie in its little adorable birdie astronaut suit. In this vacuum chamber, we toss the bird into the vacuum chamber. What happens to the little birdie?
No, it keeps going off it.
We still have gravity in the vacuum chamber.
It dies.
It goes like in an arc, right?
If you throw it up, sure, but is the bird going to be able to fly?
No, because there's no air.
Why can't the bird fly?
No air.
There's no air, and if there's no air, there's nothing for the bird to push on. There's nothing to push back on the bird. So our little birdie astronaut.
Why did you
It's
force
gonna
us
crash
to imagine this?
Yeah.
All right. So we have this concept of force pairs, right? This explains a lot of how we move through the world. Every creature on this planet is spending their life pushing and pulling on the objects around them to get around, right? So when you take a step, it's literally you pushing backwards on the earth pushes forwards on you. Birds fly, they're pushing down on the air pushes up on the birds. Creatures that swim, they push backwards on the water pushes them forwards. This is how we navigate the universe. None of us are actually moving under our own power. We're just pushing and pulling on things. If we, threw you out as the little astronaut into space, you'd just be sitting there flailing. You can't swim through space because there's nothing to push on.
Lisa,
Right?
your bone took me.
And it's important to bear this in mind. I'm going to sit in my rolly chair just to reduce friction. And if I'm sitting here in my rolly chair, and I kick the wall, I'm going to kick this wall, which direction is the force going to be in? Just point for me.
This way.
Yeah, that way. Which way am I going to go?
This way.
I'm going to go this way. Now, when I bumped into that table, an important thing that happened is you'll notice I slowed down. I was an object in motion until I hit that. But as soon as I hit it, I came to a stop pretty quickly because it applied a force back to me. I applied a force to the table, pushing on it. It applied a force back to me that slowed me to a stop. Yes.
Is that why, like, in space, you can, like, throw a wrench and you'll go that way?
Yeah, absolutely. The reason why is because when you throw a thing in that direction, you're applying a force to like this wrench that you throw. It applies an equal force back to you, so it can send you back the other way. You actually can do this on Earth. You just need to reduce your friction a bunch. So if you get yourself onto some really good rollerblades, or even sitting on a skateboard that's got good ball bearings, and hold please be careful if you choose to do this. But if you sit down on a skateboard and hold a bag full of rocks or something, a really heavy thing, and you chuck it, you will go backwards. That will absolutely happen. It is mildly amusing. Please be careful. Please don't hurt yourself. Don't throw rocks at other people.
Is that why the guns have recoil and your arms go back?
Yes! This is exactly what causes recoil. I know that we're in a place where there is very little gun shooting. I didn't grow up in a part of the world where shooting guns is much more common. And the first time I shot a gun, I had bruises, right? Because the bullet firing out of the gun, the force on that, equal force coming back on me. You're not supposed to end it with bruises if you do it properly, but like, that's how it goes. Yes, Yossi.
Does that mean that if you had a way to automatically set off the gun and you pointed it tipped down, that the gun would shoot up in the air when the bullet was fired?
Yes, and I will point out, a bullet's really lightweight. A gun is significantly heavier than a bullet. So the gun won't accelerate as much as the bullet does, because the bullet's much more lightweight.
Okay.
What happens with a rocket launcher?
I mean, yeah. Like, what's the difference between a rocket launcher and a jetpack?
Nothing.
Right? Rockets use this principle. The way a rocket works is literally, it's just a big old tube that is firing hot gas out one end. It's just throwing gas out its backside. And however much force is on that burning gas that's being shot out the rear end is pushing the rocket up. Yeah, Shep?
Does it matter like how big the gun would be? Like how big was the one you did? Is it like really big? Like
For me, it was a shotgun.
so would like a pistol be different than like a machine gun?
Yes, the larger the gun, the less recoil there is. Because there's more mass and less acceleration. Yeah. So smaller guns are actually much more difficult. All right. Do we have, one more thing I want to talk about. When I was a middle schooler, and I was first introduced to these 3 laws, I did not get Newton's third law at all. I was so confused by Newton's third law. So I want to see if any of you can pick apart, like, 12-year-old Hannah's logic. I heard this law, and it said equal and opposite. And I went, hold up. If you have 2 forces, and they are equal in strength and opposite in direction, wouldn't those just be balanced forces? And if the forces were balanced, why wouldn't the thing accelerate? Who can tell me what I had wrong? And why they are not, in fact, balanced forces?
Oh, I was gonna because
Ryan?
one is like in strength and the other is in direction and they're different forces.
Well, they're equal in strength,
Oh wait, no, but
and they're opposite in direction.
yes. So doesn't it mean like? Doesn't it like one thing goes then and the other goes back?
Oh, you're getting to it, right? You have mentioned the specific thing that makes it not work, that makes it not be balanced.
And you thought that they were going the same?
Well, I was like, okay, I don't believe this law because what you said doesn't make sense, because if that were true, then this object would have balanced forces acting on it and it wouldn't be able to accelerate. Danny, what do you think I got wrong?
Is it because it's like a reaction and a reaction typically happens afterwards?
They actually happen at the same time. It's not that one of them is first and then the other one. Both of them happen simultaneously. What do you think, Josie?
Oh, I was just asking, can I make
Yes, you can. Do y'all want to see it drawn out? Why I was wrong?
Yeah.
Wow.
So what I thought would happen, here, I'm just going to erase this. I thought it would be like, oh, I have an object here, and there's one force like this, and another force like this. So obviously they cancel out, and I'd have a net force of 0. But that's not what's happening. A 3-body diagram is one object in one moment of time. So really what's happening is there's like one thing that has a force like that on it. And then there's a different thing that has a force like that on it. There's 2 separate objects, 2 forces on 2 separate objects. So they don't balance each other out. Yeah. There's an unbalanced force on the water and an unbalanced force on the swimmer. There's an unbalanced force on the air and an unbalanced force on the bird. So they don't cancel each other out. They can't cancel each other out because they're 2 different forces on 2 different objects. Right? If it was 2 different equal and opposite forces on a single object, then yeah, that would be a balanced force. But that's not what Newton's third law means. So I just want to make sure that I hang a lantern on that one specific misconception, because it really, really made me struggle when I was in middle school. I had a whole big argument with my middle school science teacher. I was like, no, you're not explaining this well. You gotta explain this. How is this not balanced forces? Yes, Audrey?
the whole like explaining thing. That's why I felt in my old school because they would never explain things completely, and it's really annoying.
Well, I hope that whenever I am unclear, you come and ask me.